The pump hasn't failed yet, but vibration already knows it will. In real plants, vibration is the earliest warning signal of failure. In this video, I will show you how to read vibration like a pro and predict problems before they happen. Slide 1. Core idea. Vibration is not just a measurement, it is a diagnostic tool. Every fault in a pump creates a unique vibration pattern. If you understand these patterns, you can identify problems long before failure. Slide 2. Why vibration matters. Excess vibration leads to bearing damage, seal failure, coupling wear, and structural fatigue. Monitoring vibration helps prevent unplanned shutdowns and increases equipment life. Slide 3. When vibration is measured. Vibration is measured during factory testing, field commissioning, and continuous operation. Factory testing establishes baseline values. Field testing validates installation. Continuous monitoring enables predictive maintenance. Slide 4. Measurement locations. Vibration is measured at bearing housings in 3 directions: horizontal, vertical, and axial. Each direction provides different diagnostic information. Slide 5. Acceptance criteria. Acceptable vibration depends on speed, size, service, and foundation. Standards like API 610 and ISO 10816 define limits. Critical machines require stricter limits. Slide 6. Vibration components. Overall vibration gives general health condition. Frequency spectrum helps identify specific faults. Phase analysis helps determine root cause and correction direction. Slide 7. Misalignment signature. Misalignment produces high axial vibration. It often appears at 2 times running speed. It also causes coupling heating and seal wear. Slide 8. Unbalanced signature. Unbalance produces high radial vibration at 1 times running speed. The vibration pattern is smooth and sinusoidal. This is one of the most common faults. Slide 9. Mechanical looseness. Loose components create wide-frequency vibration with multiple harmonics. Vibration varies with direction and load. This indicates structural or mounting issues. Slide 10. Bearing defects. Bearing defects generate high-frequency vibration. They are often accompanied by noise and temperature increase. Early detection is critical to avoid failure. Slide 11. Cavitation signature. Cavitation produces random, broadband vibration with noise like gravel. It damages impeller surfaces and reduces performance. Slide 12. Hydraulic instability. Operating away from BEB causes recirculation and unstable flow. This results in fluctuating vibration levels. Slide 13. Directional analysis. Radial vibration indicates unbalance or hydraulic issues. Axial vibration indicates misalignment or thrust problems. Directional differences indicate foundation or structural issues. Slide 14. Transient vs. steady state. Startup vibration spikes are normal, but high vibration during steady operation indicates a problem. Only steady state values are used for acceptance. Slide 15. Real case study. In one case, vibration increased gradually over months. Analysis showed pump operating far below BEP. After adjusting flow, vibration reduced by 60%. This shows how operating conditions affect vibration. Slide 16. Reliability actions. To reduce vibration, perform precision alignment, dynamic balancing, component replacement, and operate near BEP. Trend monitoring helps detect problems early. Slide 17. Golden principle. Remember this key principle. Vibration does not cause failure. It predicts failure. If you understand vibration, you control reliability. If you want to become a strong reliability engineer, you must learn how to read machines through vibration. Like this video, subscribe for deep engineering knowledge. Lead and comment vibration if you want more real case studies. See you in the next video.